Hello there, welcome back to our discussion on the current mirror. And this time we have brought to you a special type of current mirror, which is called as gain boosted current mirror. So as the name suggests, we are basically trying to use an operational amplifier, as you can see right here, to boost with the help of the operational amplifiers gain to boost the performance of the current mirror. So the objective here is to improve the output resistance of the current mirror of the output transistor. So remember, output transistor, for example, Q2 in this circuit will have this kind of characteristics where the output current I out, which is nothing but the current flowing through this transistor Q2, and the output voltage, which is the compliance voltage here, which is the minimum voltage that we must maintain across this transistor in order to this circuit to work as a current mirror. We must drop that minimum voltage across this transistor Q2. So the characteristics is like this. You have, this is the minimum voltage right here. Okay. So this is V out minimum that we must maintain. And once that is done, you have this constant current that is equal to your reference current. I out is equal to I reference. So we have seen that in previous versions where we explained to you the basic BJT based current mirror and the basic MOSFET based current mirror, and have a look at that if you want to understand the current version, current model using OpAmp as a current mirror, and how OpAmp can help us to achieve the current mirror performance and to improve the output resistance. So when we say to improve the output resistance, essentially we want this flat curve, which is the slope of this flat curve is 0. But in practical, you have this kind of performance for the current mirror. So when you have the voltage across the transistor increasing, you have the current also increasing. And in case of a BJT based current mirror, this is due to the early voltage where the base width of the transistor gets modulated with the collector emitter voltage, collector base voltage across it. And in case of a MOSFET, this effect is called as channel length modulation, which is due to the increase of electric field across the drain and source of the MOSFET. So we use OpAmp now to make sure that we have this kind of flat curve, unlike the previous basic version, this curve. So let us have a look at how this can be achieved. So just to remind you about how the circuit will work, we see here we have used the reference, the input voltage, which is your VCC, that is the supply voltage from which I will use the resistor R to draw the current I reference. And this is the input side of the circuit. This is the input side of the circuit. Now, that reference current, which is set by this resistor R, gets splitted in case of a BJT into two parts. One is called as IB of this transistor Q1, and one is called as IC, that is the collector current of the transistor Q1. Now, the collector pin of the BJT Q1 and the base pin of the BJT are shorted together, as you can see on the screen. Therefore, I would say VCB of this transistor is equal to 0, right? That is the voltage at the collector and the voltage at the base are same. And the voltage at the emitter, I will call it VE is equal to V1. So I have used this emitter resistors here they are called as emitter degeneration resistance. We have seen the role in the previous model. So refer to that if you are new to this one. So their role is to further boost or improve the output resistance of your current mirror. And because of that, we have this voltage V1 and V2. And when you have the reference current flowing into the circuit, we say that there is a voltage that is generated across the base emitter, which is VBE of this transistor. That subsequently is used to bias an output transistor Q2, but this time we have put up an operational amplifier in between Q1 and Q2. So that's just the modification. So because of the diode connected transistor, you let the I reference flow through the transistor Q1 and the VBE is produced. And the relationship between I reference and the VBE is your basic diode model. So here is your collector current of the transistor, that is IC1, and this is your VBE one, and you have this kind of exponential relationship between that one. So your output voltage of transistor Q1, which is VB1, becomes the input voltage of transistor Q2, which is VB2. And then because of that, if Q1 and Q2 are perfectly matched, you have a production of output current that is equal to your input current. So we have seen this far. Now, the role of the OpAmp we need to understand. So what you see here, operational amplifier, which is essentially a difference amplifier, which amplifies the difference between the two voltages applied to its terminal. So it has positive terminal, which is tied to this voltage V1, which is the voltage drop across the resistor RE of transistor Q1, and its negative voltage is tied to the voltage V2, which is the voltage drop across the resistance RE of transistor Q2. And we assume that in an ideal current mirror situation, if we really have the I out is equal to I reference, it means everything is matched. The voltage at V1 is equal to exactly voltage at V2, and the operational amplifier output VO is equal to 0 because the difference between the two inputs are 0. But if there are some changes, so in a moment we will see how the transistor operation amplifier will take the action. It will take the use of negative feedback to maintain the current flowing through the RE1 and RE2. That is the RE1 and RE2 to be exactly same, so that these voltages V1 and V2 can be same. Okay, and just to remind from our previous discussion, Q1 and Q2 are assumed to be perfectly matched. It means they are of same type of transistors and they are operating into the active mode of operation. It means they are operating with a constant current across the active mode of operation. Okay, so now we also assume that the voltage at the collector pin of the transistor right here is same as the collector pin of the transistor at the Q2. So the voltages at the collectors of each transistor, they are also same. Okay, now let us assume you have this voltage VA, which is connected to the pin collector pin of transistor Q2 goes up. So it means the voltage at the collector pin of transistor Q2 goes up. It means the current through the transistor, because the voltage at the collector pin of transistor Q2 goes up, the current through the transistor, which is, let's say, IE here, goes up, and increasing the drop across this resistor, which is nothing but your voltage V2. So V2 goes up, which is coming right here, though the difference between the two, V1 and V2, goes down, and hence the output voltage goes down. Now, output voltage is nothing but the voltage at the base of this transistor, that also goes down, making sure that the current through the transistor goes down, and hence this current again goes down, making sure the V2 goes down. And therefore, whatever the proportion by which the V2 got increased initially due to operational amplifier's negative feedback, due to negative feedback that we are taking from here at the node V2 and the operational amplifier's very high open loop gain, we make sure that we maintain that voltage back to its original value. That is, V2 comes back to its original value. Opposite things will happen when the VA will go down, the voltage at the collector pin will go down, and the voltage, the current will go down, and the V2 will go down, and the OpAmp output will go up, increasing the current flowing through the transistor, and the V2 will be brought to its original value. So that's how you have a kind of maintenance of the original voltage drop. So here is the equation where we see the operational amplifier difference between the two inputs is nothing but output divided by the gain. So which is this equation right here. VB is the output voltage or the voltage applied to the base of transistor Q2. And when your current mirror works properly so that your output current is exact match to your input current, you can say that your circuit works properly. And there is a minimum voltage that required to be maintained across that output transistor is the VCE of 2, that is the voltage at the collector pin and the emitter pin of the transistor, plus voltage across the RE of the transistor. So although RE helps us to further improve the output resistance of this current mirror, the penalty is that your compliance voltage, that is the VC, is little bit increased. In the absence of RE, you need to only maintain the collector emitter voltage of your transistor across the transistor. So BJT based current mirror, since we have used the BJTs here, the output current is not exactly equal to the input current. Rather, we would say it would be somewhat less than the input current, because when you have a I reference flowing here, it is being split into two parts, that is IC, as I said, and the IB. So I reference will be sum of IC1 plus IB1, which can be written to as IC1 plus IC1 divided by beta, which is then, if can be written further, it can be written as IC1 in bracket 1 plus 1 over beta. So this is nothing but this equation right here. So this is how you see that the betas of the transistor and the base current, because the transistor BJT has the base current going into it, you have some difference between the reference current. Reference current is decreased by the beta. Okay. Now, output resistance of the MOSFET is relatively less than the output resistance of the BJT. Therefore, this kind of arrangement is often used to use the operational amplifier even with the MOSFET based current mirror circuits. And when you see the use of operational amplifier, which is called as gain boosted current mirror, these are also called as wide swing voltage mirror, because they also helps to maintain a low compliance voltage across the transistor. So you have use of RE and you have these transistors. So that's the minimum drop that you need to maintain across the transistor to make sure your current mirror will work. So these kind of current mirror is also called as wide swing current mirror. Okay, now let's have a look at the MOSFET base. This is your BJT based. This is your MOS transistor base. So it's exactly the same circuit that you see here, except the fact that the resistors in the BJT based current mirror have been replaced by the transistor M3 and M4, which are the MOSFET operating in their triode region of operation. So let me draw you the characteristics of the MOSFET, which is IDS versus VDS. You see for the applied gate to source voltage, your current rises linearly with respect to VDS, and after that it's gonna get saturated. But this region, where the region left to this line, actually where you have this linear curve, is called as triode mode of the MOSFET, where M3 and M4 can act as a resistor, which is the replacement for the REs here. And then M1 and M2, they are operating in their active mode, and same as Q1 and Q2 here. And rest of the circuit will work just as fine as you see with the BJT mode of operation. And the minimum compliance voltage right here would also be the VDS plus the voltage drop across M4 and M3 operating as the resistors. So that's your minimum voltage, okay? VRE right here. So hope you understood the basics of this video. I will encourage you to use this circuit in your SPICE simulator, pick up the components and the devices from the library, connect them together on the schematic, make sure your SPICE netlist is free of any error, including connection errors. And to do that, refer to our range of videos about using the SPICE simulator. We have so many videos with respect to that where you can actually learn. Then build this circuit, perform many analysis, starting with your DC analysis, then DC sweep, and then transient, etc. For those also videos are available. Subscribe to the channel. If you like the video, click the like button, comment on it, share with others for a wider reach, and post your comments. What would you like to see more, etc. And stay tuned for more enriching contents like this. And till then, wish you happy learning.